Hello guys. So in this video we'll be talking about CDC, clock domain crossing. So we'll be discussing everything from why it is happening, what are the issues, and we'll go through it. And everyone who is preparing for a VLSI role must watch this video so that you can have an idea, because this is one of the topics which will be asked in an interview, because they personally asked me these questions in an interview. So you might get these questions. So starting with, we'll start basic things such as what is metastability. Metastability is basically a situation where the signal hasn't assumed a stable state. In digital design, the stable states are 0 or 1, right? But due to some situations, the signal might not reach a stable state. For example, here there is a setup or hold violation. There's a timing violation, and because of that, the signal is going metastable. So, what is the issue, right? Because of metastability, what might happen? Here you can see the data fan out. Some places it is assumed as 1, some places it is assumed as 0, because if you don't drive a determined value, either it is 1 or whether it is a 0, it can either be 0 or 1. Sometimes it is assumed 0, sometimes it is assumed 1. If this is what is transmitted in the downstream logic, then obviously there will be indeterminate design behavior, right? So that's the issue here. Is it avoidable? No, you can't avoid metastable state. Basically it will happen. What you can do is mitigate it. So we should think about the mitigation strategies now. So before going to mitigation strategies, one of the questions you may get is the causes. What causes metastability, right? It can be a wide range of reasons, such as the setup or hold time violation, asynchronous crossings. It may be clock quality issues like jitter, like delay cycle distortions, skew between the clock tree branches, or it may be dynamic conditions like PVT, DVS, or it might be as simple as something like aging. For example, because of aging, the path delays increases usually, and this path delay, for example, a signal had to reach by this edge, let's say, of some clock, right? But because of aging, this signal might get extended, or situation something like this, like this is due to aging. These situations may lead to metastability. So we will be discussing about the methods which we can use to mitigate this metastability. So that's where in synchronizers come in. What are synchronizers, right? Synchronizers are basically a type of setup which will help you mitigate the CDC issues or the metastability issues, to be more particular. So let's talk about synchronizers. So here you can see a basic 2-flop synchronizer, right? So this, let me go through the waveform, and we'll be talking about what a 2-flop synchronizer is and everything. So starting this flop here, right? This flop is called as the launch flop, and these flops here are called as the capture flops. Just a minute, I'll write it down. Capture flops. These are the launch flops. Okay, this is in A clock domain, this is in B clock domain, they are asynchronous. So let's assume the waveform here. See, the A dat is being transmitted and it is being captured at the B clock. So what is happening here is, at this edge, at this B clock edge, we are sampling the data, and because of some setup hold violation, it is going into a metastable state, and we are sampling it at BQ1 data, a metastable data. But this value, if we give it one more clock period to settle, right, by now it would have settled to some value. Here it is going metastable. By this time it would have settled to a value, and this value I'm sampling it. This clock edge is the BQT clock edge where I'll be sampling. This clock edge is the BQ1 clock edge where I'll be sampling. So basically what synchronizer does is, basically it is giving the signal time to settle to a stable value. We are not removing the metastability, we are just allowing the signal some time to get stable. Okay, so is it always required to add these synchronizers? The answer again is no. Quasi-static signals, right? Quasi-static signals, they do not change during runtime. If the signal itself is not changing, and you will be sampling the same value anyway, why do you need to add a synchronizer? That is one of the basic things. And if you are confident that the signal will pass without any metastability, some designs may actually have that, then it is not required to add a synchronizer in the path. Okay, so one of the most important things you guys need to note is using spyglass or VC spyglass, right? This, you need to have experience using spyglass or VC spyglass. Here, the path analysis will be done by the tool, and it will throw all the signals which are crossing one domain to another. This tool will help you learn about the actual CDC issue. There are something called tags, right? If you have used this tool and you know how to solve CDC issues after you go through these videos, series of videos, it will be helpful for your placement. So yeah, moving forward. So after you listen to what I said just now, you should be having the thought key. You are saying that we are not avoiding metastability state. We are just allowing the signal, giving the signal time to settle to a certain value. What if it doesn't settle between this time period, this one clock delay which we given? What if it doesn't settle? Right. If you had that question, you are right. Sometimes the signals don't settle within that time. So there's something called mean time before failures. This is a calculation. Some designs, right, which are very high speed designs, they require more than one stage of synchronizer. You can see here, this is a two stage synchronizer. I mean, 3 flops are there. So what is this mean time before failure, right? This gives the probability of if the mean time before failure. What is mean time before failure, right? Mean time before failure is a calculation which you can do to know when the signal can reach a metastable state. So this is a very simple formula where the frequency of the clock is taken, where the inverse of the frequency of the data is taken, and some other factors are present. So if the clock frequency is higher, then the chance of metastability increases. If the data changes more frequently, then the chance of going metastable becomes more frequent. So if the mean time before failure is very small, then that means your chance of going metastable is high, right? Because it's the inverse. If mean time before failure is high, then the chance of going metastable is low. So you need to, if the data is not getting settled within a single flop, you add another flop. But this is a very dangerous thing because it adds a lot of latency to the design, right? If a lot of latency is added every time you add a flop, so you need to calculate mean time before failures and judge whether the signal will become stable or not, and then move forward, right? And then the next question you should be having is, basically we will be sending signal from one domain to another and we'll be capturing the register version of that thing. So is it required to register or synchronize a signal in the sending clock domain before you transmit it, right? Yes, it is usually a very good practice to have this. Why? Because there is something called combinational settling. Here you can see combinational signals take time to settle and they change a lot. Here you can see, and we know that when a signal changes and it changes near a clock edge, that is what might lead to a metastable, right? If in the previous we have seen MTBF formula, what was the formula? It is indirectly proportional to the frequency of the data. So data change. So if the data is changing more frequently, then there is a more chance of this signal going metastable. See here, because it is changing more times, here it is going metastable, here it is going metastable, but it is reaching a settled value. So how can you avoid it? Just register the version, right? There's a COM signal here, you register it. At the clock edge, what was the value? 0. That is what is there in the signal, right? Same here, at the clock edge, what is getting sampled? 1. It will be driven 1. Same here, it is 0 at the clock edge, so it will go 0. Now you can see here, just by seeing, you don't need to be a max wizard to know this. Here you can see the frequency of the data change, and here you can see the frequency of the data change. So which is better? The second one, right? The register version. So yeah, that is why usually it is suggested that You register the signal and then transmit it to another clock domain. But sometimes because of some architecture constraints, right? If you are working and you have some experience, then you might know this, that sometimes every clock matters, like every core clock or whatever it is, every clock, every latency matters. As I was saying, there might be very stringent constraint requirements or architecture where, for example, if you increase even one more core clock, one more clock cycle, if you use, it may lose the IP, or the system level design may lose the competitive edge it has over its competitors. So usually these decisions need to be taken with a lot of thought process. So yeah, people, basically we have just started about clock domain crossing. In the next video, we'll be covering what happens when a signal passes from a fast clock domain to a slower clock domain, and we'll see how to mitigate those issues and all. So stay tuned, and if you have any queries or doubts or any changes in the videos to be made, please post it in the comments below so that I can make those changes, and you can get more quality and better structured data. So yeah, this is a small effort from my side to have some playlist for the students from EC domain so that they can prepare for their placements. So yeah, thank you.